Hi, Steve.
Hi, good morning. How are you?
Good morning.
Good morning.
Morning. I'm just gonna finish this today. We'll look at how we can assess a logistics.
Steve, could I just ask, is this what we do because this is a different pathway, isn't it? Is this more linked to the data project or to the actual exam, like certification?
Okay. The situation is. Oh, hang on. Yeah, my microphone's a bit loud here. Yeah. It is linked. We've now completed all of the work for the AI 900 certificate. I'm hoping that there will be a revision session next Wednesday, and we should get I'll get some material you can use to revise over Christmas. The planned date for the exam, I have to get it agreed with Dr. Rice still, we're looking at the first week back after Christmas, so on the Friday possibly. That will give us a few days in that week to get us back up to strength again with the AI 900 certificate.
Okay.
But
That's
what
on
we're
the
doing,
7th.
yeah, well, it's not set for that. I have to get that agreed because obviously there's some administration associated with doing the exam. In the meantime, we've been delving a little bit deeper using a different pathway into all of the things that we did using the studio and the designer for the AI 900, but looking a bit deeper into the code that's involved in running those processes and, more importantly, assessing them.
Okay.
That's what we're doing now, really. So, and that's where we've been for a couple of weeks.
Yeah, so I'm just catching up on some of this week's lessons.
That's
I
all right.
just wondered if it was linked to the actual certification.
No, it's not.
Okay.
No, we finished that a couple of weeks ago.
Do you know when we're doing the other exams at all?
I have sent an email to Dr. Rice this morning asking exactly that question.
Okay, perfect. Thank you.
Hopefully, as soon as I know, you'll know.
Okay, perfect.
Okay. I don't know if it's going to be before Christmas or after Christmas. If it's been confirmed or communicated to you all yet when the cloud and the Excel exam is going to be. But I'm definitely pushing for the AI 900 to be done after Christmas to give you some time to revise for it, and I will give you some revision materials as well. But we're hoping to run a special session on Wednesday. That's certainly in the plan. And I've trying to find out who will send you the team's invitations for that. So hopefully we'll get that information very soon. Logistic regression model. And the link is this one here, which I'll put into the chat. There we go. So that's the current link. That's where we are right now. Hopefully I'm sharing. Yes, I am sharing my screen. I'm sorry, which? Oh, just the BCU. Yeah, that's what I use. It should show you the home page, the logon page. Okay, so I would restart your machine and it will automatically find the network. Okay, we'll start in about a minute.
Good morning.
Good morning, Ritu. So we're going to continue where we left off yesterday, looking at logistic regression models. We'll start in about a minute or slightly less, and then we'll move along with it.
Steve, I'm going to drop off the call because I'm just catching up with the other lessons this week.
Okay, I loaded yesterday's lesson up into the Dr. Rice's YouTube channel as well. So if you can't get it
Perfect.
from General, it's on the YouTube channel.
Okay, thank you.
Okay, no worries. Okay, let's begin. Oh, by the way, if you see my mouse moving over the screen and me not saying anything, it means I haven't switched my microphone on. So if you could remind me when that happens, that would be very useful. Thank you. I often talk to myself, but I try not to do it too often. Right, so I think we're going to have to activate our sandbox. Firstly, we're all on this page, yes? Everyone's on this page. I sent the link. Good. Let's activate the sandbox. I'll just wait for you to. You're on your eye? Okay, right. So activate your sandbox then. Sandbox activated. Oh, 2 hours. So in the previous exercise, we fit a simple logistic regression model to predict the chance of an avalanche. This time we'll create the same model, but take a deeper look on how best to understand the mistakes that it makes. Okay. So all the usual in terms of what we're going to install, what data we're going to use, the graphing we're going to use, and using pandas, read CSV with a delimiter of a tab. We take that in. I'm having a lot of fun at the moment, moving between panda arrays and numpy arrays. Numpy arrays look at anything in a location as a 64-bit float, a number. So even if there's text in it, it just crashes. And unfortunately, the panda arrays have to have row and column headers. Otherwise, again, they don't work. They also mysteriously put an extra comma at the end and put the index in the front. So in my project, I'm having to convert continuously between panda and numpy arrays because some of the specialist applications I've got only work with numpy arrays, not panda arrays, and vice versa. I've got some that only work with panda arrays and not numpy arrays. And I can tell you over the past few days, it's driven me just a little crazy getting these to work together properly. But I think I'm just about there. Anyway, so import the data from a CSV file using that. Yes, good. So let's have a quick look. Let's print the first 5 rows, and let's have a box and whisker plot so we can see the difference to see how the avalanche relates to weak layers. Okay, to see how closely one explains the other. Let's have a quick look. And we saw that weak layers was quite a good indicator of an avalanche. It kind of makes sense. Let's look down a bit. So there's my first 5 layers, first 5 rows. And that's of my data set. And then this is, again, these numpy indexes drive you crazy. It's good if you want to delete a row though, because you can just use it, delete the row by the index, and that actually works quite well, but it doesn't help you because the headers aren't on a row. So, very complex. So 9 weak layers. Tracked out. Did we ask for? We asked for. We asked for the chance of an avalanche. 00101 00. Yeah, okay. So tracked out means the chance of an avalanche, because if you copy, sorry, whether or not an avalanche occurred. So if we've got this, so as we'd expect, that matches that, because that's what we're looking for. So the tracked out column is what you're looking for, in which case we're checking to see if there's a Boolean on the avalanche. So let's have a look. Our weak layers are 9, 6, 8, 10, and 9. It seems that the avalanches are associated with having more layers of snow. If, for example, there was no overlap between this, then you would say that they weren't related. If they were absolutely 1, 1, like this was shifted up here, then you could say that they were highly indicative. So, and it makes sense that if you've got a weak layer of snow, it's likely to slide over the layer of snow underneath it. That said, many weak layers have been recorded, but no avalanche occurred. So there are other factors. So this means our model will have difficulty being extremely accurate using only this feature. So let's continue for the moment and come back to this in a future exercise, which obviously will include more features to see if our model is improving. But before we begin, we need to split our database as usual into training and test sets using the train test set split. And we're going to do it 75-25, where the test is 25% and the train is 75%. Starting off with this random state. Have a quick look at the shape of our training and testing. So we should come up with however many rows we had, divided in a ratio 25-75. Just run that. Yeah, and we see we've got 821 training and 274, so that's 3/4 and a quarter, as we'd expect. Okay, so now we're going to fit the model. The model we're going to use is this formula.api as SMF. So we're going to use logit, which is our logistic regression, where avalanche is explained by weak layers, and we're using the training set, and we're trying to fit the training set into the idea that the avalanche is explained by weak layers, and then when we get our model back, we just know that it's trained. So that's done. Current function value 0.6, iterations 5. So yeah, that's not bad. It's just come trained quite quickly. So there's a very strong correlation between the two, I think. So assessing the model with summary information. Yeah, you can always ask for a summary of your model. And as we know, we can also save the model to a pickle file and so on. So there's our summary. Observations 821. These are all quality metrics here. And I think that is the mean least squared error that's being used here. And did it converge? Yes, it did. And we ended up with, that's interesting. So we've got an intercept here. and for weak layers. Okay, so summary provides us with some detailed information. Two useful pieces of information are in the bottom row. The coefficient for weak layers is positive, which means as weak layers increases, so does the probability. So it's positively correlated. The p-value column is less than 0.005, which means the model is confident that weak layers is a useful predictor of avalanche. Yeah. So again, these are quality and confidence limits. How can we look at it visually? Sometimes, but not always, we can visually assess a logistic regression model. Let's plot our model against the actual data, and then we can see how well it's performing, sort of visually. So again, we've defined our own little user function here, which is simply going to return the model prediction where weak layers actually equal is our weak layers. So we've got the actual weak layers as against the here of our test numbers. So these are going to be what we're going to the actual values that actually happened in the test set. So these have not been seen by the model, but they are versions of weak layers and avalanche. And we've got our trend line here. We're going to predict it back and plot it. So this should just show us the difference between our data points against our logistic, and you can see that it looks like it's completely unsuitable. So it's hard to see the S shape of the trend line because the number of weak layers of snow and the likelihood of an avalanche is only weakly related. If we zoom out, we can get a slightly better view. So we put in a different range. And now our values now exist all in here. Weak layer 0, avalanche is 1. Here, weak layer 6, avalanche is 0. So these are the extremes. And what you can say is if we're in this range up to here, then we've got a good chance of an avalanche. So this is a smaller chance here. So you're more likely to have no avalanche. But there's never this. If this line kind of was much lower, that would be much better for us, because that would actually say to us, look, we've got an offset here. Even with 0 layers, we've still got what looks like a 30% chance or 25% chance of avalanche, which is not great, really. So clearly, there's some information. I mean, it's useful to see it like this because you can interpret it now. You can say from here, these are all the chances really of where I'm going to have an avalanche. And of course, when I'm here, when I've got 10 layers, you've got an exceptionally high probability of an avalanche. Yeah. But if you've got no layers, you've got a much smaller probability of an avalanche. Sorry, smaller probability of an avalanche, but a greater one. It's much closer here to there being no avalanche. And this is our informative shape. But we can see, but checking the earlier graph, we can see that our model will predict an avalanche when the number of weak layers of snow is greater than 5. Okay, because 0.5 at x equals 5. So let's have a look at that. So here, this is at this point, you're tossing a coin for probability of there being an avalanche. 0 and 1 are the possibilities of tossing a coin. But this is saying that if you're in this region, then you will get an avalanche. you're likely to get an avalanche, and if you're in this region, not. So if we set our decision point to be 0.5, then the problem with setting it at a single value is that it takes a very small change in order to push it over that margin. So what you really want actually is a kind of no man's land in between where you're not certain, and you can apply it. So you've got a margin in the middle. So how this relates with the points is hard to tell. As the points overlap, so it's difficult to see how many points there are at 0 or 1. So how can we assess the model? Well, we can look at its cost function, and we look at the log of the cost function, purely because it's easier to scale. So let's assess our model with the log loss cost function. So we're going to import log loss, make the predictions as before, and then calculate the log loss on these predictions using the avalanche characteristic of our test set. I'm going to end up with this. So the log loss is 0.680, so 0.66, yeah. And what does that mean? Well, this could be useful to compare two different models, but it's hard to get a grasp on exactly what this means for a real-world performance. So what we're going to do is test classification accuracy. So we're going to use NumPy arrays for that. So first three predictions, ILOC is a way of referring to the individual rows. So we're looking at the first three predictions: ILOC 1, ILOC 0, ILOC 1, and I'm sure it will say beyond here ILOC 2. Yeah, there you go. So that's the first three rows. And we're going to convert these to absolute values and basically say if avalanche predicted equals predictions greater than or equal to 0.5. So we've actually set a logical condition here that says an avalanche is predicted, which is a state, if your predictions are greater than or equal to 0.5. We added that yesterday, didn't we? We added the greater than or equal to. So now they put it in. So print a few predictions, converting into categories. So by the category, we're talking about whether it's predicted or not predicted. So let's run that. It's simply applying a threshold. So our first three predictions are 0.78, 0.6, and 0.5. And the first three predictions are therefore true, because 0.7 is greater than 0.5. True, because 0.68 is greater than 0.5. And true, because 0.56 is greater than 0.5. So there we go. That was pretty straightforward. And so now we're going to look at calculating the accuracy. And the accuracy is, guess what's correct, is when the test avalanche column, which is our actual data, matches our avalanche predicted column. That's all we're asking for there. That gives you a state of guess was correct. And the accuracy is the NumPy average of all of the guesses that were correct. Okay. And then we get the accuracy for the whole lot. So basically, it's the average correct guesses, which is the number of correct guesses over the total number of guesses. And we've got the accuracy for our whole test set was 0.616. So that's what, so 61% of the time or 62% of the time we were correct using just number of layers to predict avalanche. Not very good, because tossing a coin will give you 50%. So it looks like predicting the correct answer 61% of the time. Yeah, this is helpful. What kind of mistakes is it making though? Let's take a look at whether it's guessing avalanche when there are none false positives. So now we're looking towards moving towards what we did in the ML Studio when we had our little confusion matrix of false positives, false negatives, true positives, true negatives. And then we can get our recall and our F1 score from that as well. So that's all taking us back to what we did before, but let's run it. So wrongly predicted on average 21% of the time, failed to predict avalanches 17% of the time. So I think it's more understandable than what the cost function is of the graph. Yeah, it's interpreted the cost function, isn't it? By simply comparing the declaring a false positive under these conditions. So a false positive, let's look at these because it's quite important, I think. A false positive is the logical condition that there shouldn't have been an avalanche and there was. So it's an and situation here. So if that happens and that happens, so if we're saying it's not guess was correct, ANDed with, and that's logical ANDed, which means if they're both true, you will get false positive, which makes sense. It means that there shouldn't have been an avalanche, but you've predicted one. And a false negative was, we just simply put a not here in front of the test avalanche. That's all we've done. Everything else is the same. So that's saying a false negative means that we said it wasn't going to be an avalanche when it should have been. So both of those are mistakes. And what we can do is that we can express those as the average of all of those events. And from that, we get 721.16 and 17.15. And we could certainly put that on a confusion matrix. So we walk through different ways to access a logic regression model. We've seen that detailed summaries can provide rich information, but it can be difficult to digest. Metrics for these kinds of models aren't necessarily intuitive or detailed enough to understand the model. With a little extra work, we can look at actual predictions versus actual outcomes and get an intuition for how the model might work in the real world. Okay, so now next unit is how we can improve our classification model. What can we do apart from just picking in a different algorithm? So have a read of that for a few minutes, and obviously providing additional features is one, and making sure those features are independent if you can. So have a quick read. I shall mute my microphone and I shall remember to Okay, so we can just confirm this, that we found that our model could predict avalanches to some degree, but it was still wrong about 40% of the time. Remember, tossing a coin is only 50%. So this error amount is because our feature, the number of weak layers of snow, isn't the only thing that is responsible for avalanches. If it was, then we wouldn't have had when there were 0 layers of snow, you still had a 30% chance of or 25% chance of an avalanche. That always is a kind of an indication that there must be other factors at play, logically, that's causing the avalanche. Now, we may not have that information. We might not even know what that factor is. It might be Bigfoot. Who knows? But we know that there is other information. So there's 2 ways to improve the classification model performance that we're going to look at. Obviously, providing additional features and being selective about what enters the model. Yeah. So the most important thing is that those features are indicative, so that they do indicate the outcome. And 2, the assumption made by logistic regression that these are orthogonal, so they're mutually independent, that one does not depend upon another one, is not always true. And therefore, we have to take that into account. So it combines the features, as independent, meaning it assumes the features don't influence each other. For example, our model will assume the amount of snowfall doesn't change how many people will visit the trail. By default, it also assumes that snowfall increases the risk of avalanche by a set amount, regardless of how many hikers are walking on the trail. It's hikers that will disturb weak layers of snow and cause the avalanche. And your model needs to be able to deal with that. And ours currently doesn't. It's perfectly happy to predict an avalanche when nobody's on the snow. It's interesting. So internally, logistic regression combines these features. It also assumes that snowfall increases the risk by a set amount, regardless of how many hikers are walking on the trail. So what are the good and the bad sides of independent features? Well, logistic regression can be told to combine features so that how they can work together can be modeled, but won't be by default. So we have to tell logistic regression when something is dependent upon another thing. So and most of decision trees don't make that, and most other algorithms don't make that assumption. It's not, well, yeah, I won't say most, but a good few. The fact that logistic regression treats features as independent by default is both a strength and a limitation that should be kept in mind. So it's easier to make clear predictions, such as increasing the number of people increases the risk, which cannot usually be done with other models. It also reduces the chance of overfitting the training data. By contrast, the model will fail to work well if its features actually interact in the real world. For example, 5 hikers crossing a mountain is risky. If there is snow but 5 people is safe and there is no snowfall to cause an avalanche, a logistic regression model needs to be told explicitly to look for interaction behavior between snowfall and a number of hikers. In this example, to pick up this nuance. So the message is, think about your features. Are they really independent? Another way to improve your models is to give a real thought to which features are supplied and why. Generally, the more features we add to the model, the better the model will work. However, this is only true if the features provided are actually relevant and explain something that existing features don't, i.e. they are indicative of a part of the outcome. May not be all of it, but at least a part of it. example, if we only had daily records of the amount of snow and the number of hikers and the number of birds spotted, the number of birds spotted is probably not relevant information yet. If supplied, the model will end up modeling a relationship between avalanches and the number of birds on given days. If all birds were spotted more on an avalanche days, the model will suggest birds could be responsible for causing avalanches. We might then set up a systematic bird watching program to predict avalanches, only to find it doesn't work at all. Yeah. So again, this is the difference between a correlation and a causation. It comes down to that. They appear to be one causing the other one, but it's not. They just happen to be occurring at the same time. And any relationship, see, the model will try and make a relationship out of the data, and only if it's really truly random will it not be able to do that. It'll have a stab at some kind of probability. And it's interesting when I was talking to somebody a little while ago, not that long ago, about how modern research often works, which is that you make your hypothesis and then test it. And then you'll find that your data doesn't quite match that hypothesis, your results. So what you do is you modify your hypothesis to maybe capture something that you've noticed from the results. And then you keep doing that until what happens, usually by some random event, there is a complete correlation. And your model seems to be, at that point, totally justified. And you publish, as to say, these are my results. Didn't they show what I said would happen? And this is such a problem, and been such a problem in research, especially medical research and psychological research, over the past 10 years. But now the most prestigious journals make you log your hypothesis before you start your paper, so that it's not possible for you to move your results towards your original hypothesis. You're not allowed, they won't publish you if you change what you said you were looking for at the end of it. So, and it's a way of improving the robustness, really, because eventually randomness will produce sensible outcome. For example, there is a 10 to the 39 possibility, and it's 10 with 39 zeros, that if you knock a drink onto the floor, that drink, even if its cup got broken, in the next second, that would reform itself back on top of the table. The time would go backwards. 1 in 10 to the 39. So there's an actual possibility that time can go backwards, but it's very small. And it's like that with data. So avoiding undertraining, using features naively, can also lead to undertraining and not make predictions as correctly as possible. For example, temperature and the number of hikers might be both strongly linked to avalanches, yet if people only walk on sunny days, the model might find it difficult to differentiate how important hikers are in comparison to temperature. Similarly, we probably find that our model works better if we supply our number of hikers as an exact count of visitors rather than simply high or low. So the model training can find a more exact relationship. Yeah, binary values aren't great as inputs, because it only partitions half the space. And if a model is trying to learn which half of the space to use, it's very, very difficult. Whereas if it's got a whole range of values, it can then see how those values change and compare it to how the outcome has been changing in the test, and then see how much of it wants to include in the model. So it's all about, and we can find a more exact relationship. So let's improve our classification model. We've still got our sandbox here. So we're going to improve it. Let's see how. So let's load our data up as before. I'm not going to go through it because it's pretty much the same. We get our shape of the training and testing, and we print the first 5 of our training sample. Okay, so there's this is what we predict for our testing sample here. Not very good because there's only one avalanche predicted, but these are picked at random. And let's see what happens. So we've got numerous features available. This is how disturbed the surface to the snow is. So I think that's an interesting one. Fresh thickness is how thick the top layer of snow is, or 0 if there's no fresh snow. Wind is the top wind speed that day. Weak is the number of weak layers. No visitors is because the number of visitors is the number of hikers who were on the trail that day. And tracked out is 1 or 0, means that the snow has been tramped heavily by hikers. Okay. Snow has been trampled heavily by hikers. Okay, let's see how that correlates. Let's make a logistic regression and assess the performance with accuracy. What are we looking for here? We're looking for how avalanche is explained as with weak layers, and we're calculating the accuracy based purely on weak layers. And we get accuracy, as before, 61%. So that's where we were. So let's bring in some more features. Now, most of our features seem like they could be useful, at least in theory. Let's try and model with all the features that were available. So we're looking here where the avalanche on a logistic regression is explained by weak layers and surface, how much it's been trampled, the fresh thickness, sorry, not how much it's been trampled, but what the surface is like, the fresh thickness and the wind and number of visitors and whether it's been trampled down. And based on our train sample, we're fitting it to the model. So we can add as many features as we want, obviously, but they must exist in the model. Oops. Oh dear. Train fair, that's what we started with. Multiple features, we are here. So we're going to try training with all the features. So as you can see, it's worse. That's a big improvement on the simpler models we've been dealing with. But the accuracy is less, isn't it? The accuracy was 0.7 before. Let's just check if I've done it right. So this is training it just on weak layers. And we've got this with our accuracy of 61%. Then we used multiple features, and I thought here we go. We can improve our model using multiple features. And that's all of it. And we run that. I just want to be certain it's true. There you go. So no, the accuracy has gone down. I thought it was a fluke, but it's not. So they're saying that's a big improvement on the simpler model. Why is it a big improvement? Accuracy is less. This is what happens, you see, when you've got randomness in your process. So let's look. Yes, someone's got something sensible to say.
Because now accuracy is 78%. Isn't it more than before then?
Oh, of course. Sorry.
Before accuracy was 61.
Yeah. No, you're absolutely right. Yeah, it's gone up, isn't it? From 61% accurate to 78% accurate. Yeah, I was thinking about the other number. Yeah. Yeah, okay, so it has gone up. Yes, big improvement. Yeah, up to 78%, taking into account all the features. Now, the question is, can we take out some features and get a better accuracy of model? So that's all the features summary. Let's see what we get. So on all of our features, we've got all these lovely things here. Where's our P0 values? Yeah, see, these are seriously important values. Whereas this is less important, and that is less important. Yes. Okay. So we look at the P column. We call them that values less than 0.5 means we're confident that this parameter is helping the model. Both surface HOAR and wind have very small values. So we're looking here. Wind is 0, meaning that they're useful predictors and probably explain why our model is working better. If we look at the coefficient, which states parameters column, we see that these have positive values. This means with higher winds, the greater amount of surface is a higher avalanche risk. So the weak layers is important, that's important, the wind is important, and number of visitors is fairly important, but whether they've trampled the snow or not isn't. Very interesting, isn't it? To look at that. And the most recent thickness of snow is not important. I guess it's because an avalanche requires more than the fresh snow to be unstable. All the layers below have to be unstable. So that's why it's about the layers of snow. Okay, so we're going to simplify our model. My guess is by simply taking out everything except for the surface HOR, the number of visitors, and that's it. So, oh, we're not keeping the wind in. Oh, here's the wind, yeah. So we've got this, the wind, the number of visitors. So basically, everything that's a 0 in here, that's one of our quantities, almost 0 in that case as well, we're going to keep. And we're going to throw out the things with the p-values greater than 0.005. And that's simplified our model. And let's see what we get for that. So we're still only at 78%. So our new model works very similarly to the old one. In some circumstances, simplifying a model like this can even improve it as it becomes less likely to overfit. Yeah. That's the idea. The idea is the way you can avoid overfitting is that you want the minimum amount of features that explain the maximum variance of the data set, because that means that you're not specifying lots of features that's absolutely tracking the training set. What you're doing is trying to get what the essence of the training set is. What are the real most important features in that training set that are basically going to be in all of the ones that are supposed to be classifying to that particular point. So careful feature selection is important. So usually we don't just pick features blindly. let's look about what we've just done. We removed much of the fresh snow, removed how much fresh snow was in the model, trying to predict avalanches. Something seems off. Surely avalanches are far more likely after it snowed. Similarly, the number of people on the track seems to be unrelated to how many avalanches there were. But we know that people can often trigger avalanches. So our model's not quite logical. Let's look at the summary again. See if we can see why. Look at fresh thickness. We're told it has a negative coefficient, which means as thickness increases, avalanches decrease. Similarly, visitors has negative coefficients, meaning that few hikers means more avalanches. So this is how they are related to each other, related to whether or not there's an avalanche. Similarly, how can this be? Well, while visitors can cause avalanches if there's a lot of fresh snow, presumably they cannot do so easily if there's no fresh snow. This means that our features aren't fully independent. Yeah. If you end up with one going up and one going down, you can be sure that there's a connection somewhere. We can get the model to try and take this into account by using the multiply sign. Let's try that now. So what we're going to do is we've now created a new feature. We've got weak layers, the surface HOR plus the wind plus this new feature, which is visitors times fresh thickness. And that helps is that number of visitors? Yeah, number of visitors and fresh thickness. So fresh thickness is a minus, number of visitors is a minus. When you multiply them together, you're going to end up with a plus. So model with interaction, again, just as before. Let's see what we get now. So we now combine them using this multiply sign. And what we've got now is up to 83% accurate. The model has improved to 84% accuracy. Let's look at the summary information. And we're seeing our coefficients now. Weak layers is strong, positive, number of visitors. And this is our new feature here. Number of visitors combined with fresh thickness. That's our new feature. And it has the interaction term is helpful. The p-value is less than 0.005, which means the model is performing better than in previous attempts. So we've still got the number of visitors in, still got the thickness, but by combining their effects, before they didn't explain the model, and now combined together they do. So that's a powerful feature. Can we do any more? Very quickly, let's explore what this means by looking at the model predictions. So with our new combined weak layers wind, so we're going to look at two independent variables, two independent features, weak layers and wind, and see what that looks like as a 3D plot. Still executing. Still executing. I guess there's quite a few samples in there, isn't there? Okay, we've got our plot. Beautiful. Look at that. So here we go. We've got our wind, our weak layers, and the combined probability. And there's our extended curve. This graph is rotated and explore how there's a clear S-shaped relationship between the features and the probability. So we might just be able to just drag that and turn it around. That's not bad, is it? That's in 2 dimensions. You've got the 2-dimensional S going on there. So you can look at it from the purple's point of view, and you've got an S. You can look from the orange's point of view, and you've also got an S. So yeah, you can rotate this around, cut a plane through it. Quite a powerful idea. This all comes from Plotly, which is really good features. Okay, so let's look at the features that we said can interact. No visitors and fresh thickness. And that's very pretty, isn't it? So we can see that there is a direct correlation here. That this is our fresh thickness. So really, the thicker the snow, the fewer the visitors, because they're not visiting to to ski, they're visiting to walk, most of them. So it looks quite different from the other one. So from any side, we can see an S shape, but they're combined in strange ways. We can see that the risk goes up on days with lots of visitors and lots of snow. There's no real risk of avalanche when there's a lot of snow but no visitors, or when there are a lot of visitors but no snow. So we need both the X and the Y, this one and this one, combined together to peak with the probability on the Z axis. There. So down here is a part of the curve that says no visitors. So that's a large number of visitors, but no snow, and there's a low probability. And over here, we have no visitors, but a very large thickness of snow. So that's what this is predicting. And if you get both together, see, this is a classic kind of AND function. So it looks quite different from the others. So we can see that, the fact that it shows higher risk when there's no snow could be good due to rain, which keeps visitors and snow clouds away, but results in avalanches on the older snow. To confirm this, we need to explore the data in more depth, but we're going to stop here just for now. And we're going to have a quick knowledge check. So let's recap. We've improved our simple model by adding more features. That's a key thing to do. But the predicted interpreting our model coefficients parameters from the model accuracy. So looking at the model coefficients, we can see that its importance as a feature, and the eliminated unnecessary features, so ones that had low coefficients and very high p-values. Something's got a higher p-value, then you don't want to go anywhere near it. You explored how sometimes it's important to think about what your data really means. And the idea of combining features is a very powerful idea, because then you get the relationship, especially when they appear to be dependent upon each other in some way. Then you just simply combine their overall effect. You know, if you know that one is actually fairly closely related to another thing, then just create a new feature that combines their effect, and then just use that as your standard, and it's part of your standard set of features. And in fact, what you can do is you can investigate whether or not things are connected to each other by combining them and seeing the results to see if it does improve. Knowledge check then. Nice and slowly. Think about these. What's the difference between classical regression and classification models? What do we think? Have a think about this.
Class means grouping, and regression
Yeah,
is
class is grouping. Yeah, regression is values. Yeah. Yeah, so we're going to go for the third one. Classification models provide labels, such as cherry or banana, but regression models calculate continuous numbers. Let's try that. How can we improve real-world model performance?
Second one.
Yeah, I think it's the second one. We not always by adding features, but by adding and removing can be useful depending upon the situation. If they're related to each other, for example, and you can combine features. What is one reason why logistic regression uses log loss rather than more intuitive cost functions? Log loss is stricter about model errors. Yeah, log loss really punishes errors. That's what it does, which is good in a way because it enables you to really zoom in on in the area you should be. The problem with log loss is that nowhere near convergence. It's not very helpful. It's good if you're already close in, but you need to be fairly close together before it's useful. So quickly check then. So log loss is stricter. See if we're right. Are we wrong? Yes. Hey, collect the points. Move on. Okay. So there's our summary. And I think we'll take our break then, because it makes sense. And we'll come back in 20 minutes and look at the next module. Okay. See you in 20. Okay, so looking through the summary then, I think we're pretty clear about what we've covered. And most importantly, including those that try to predict more than 2 possible categories. Okay, so let's unlock our achievement and continue. So, random forest is one of those algorithms that's very powerful but very sensitive to its hyperparameters. Fortunately, there are several methods which have been implemented in the various package providers to find those values for us. That's often the way with packages. You start off with that you need to find these hyperparameters, and then someone produces a research paper that says this is a good way of doing it and this is a better way of doing it, and it keeps going on about hyperparameter selection. One particular clustering mechanism, dbScan, again very powerful but very sensitive to its starting parameters. And there are lots of research papers out there right now offering ways to optimize those parameters and find them so that the application is more successful. So, more complex models can often be manually customized to improve how effective they are. Through exercises and explanatory content, we'll explore how altering the architecture of more complex models can bring about more effective results. So we're going to be looking at discovering some new model types. Well, they're not quite new to us. Learn how they can affect performance. Practice working with hyperparameters to train. I just want to make sure that that is the next module in the system. So we're going to go back just to check here. Just want to make absolutely certain. This one. And we did option 1. And let's have a look at the pathway. We are here. So that is the correct place. And we know we're here because it's the one that's got that isn't green on the experience points here. These are all green, which means we've completed them. So we are in fact at this moment here. So let's start. Have a quick read. Predicting Olympic results using machine learning. Oh, that'll be fun. Okay, so you've got to hang on to this. We'll go through it slowly, try and understand the models as we go. So we're going to look at the features, physical features that people have that can predict who wins the medal. rhythmic gymnastics. Okay, so let's look at decision trees and the model architecture at the bottom of this page. Sorry?
Would you be able to paste the link, Steve, on the chat
Yes,
window?
of course.
Thank you.
Of course. So that's where we are. And we're just about to hit the continue button when we've all at that point. Okay. So let's hit the continue. Decision trees and model architecture. So I think it's probably better if you just read that to understand what a decision tree is. We kind of showed one, didn't we, on its side? But this kind of explains it. And pretty much all these trees, forests are all based on this basic idea. Okay, so let's look to see how they're trained. They're trained one node or decision point at a time. At the first node, the entire training set is assessed. From there is a feature is selected that can best separate the set into two subsets that have more homogeneous labels. For example, imagine our training set was as follows. We're looking at weight and age as a feature. There are our two features we're considering, and whether they won a model is our class, what we want to classify things to do, to say whether or not we win a model. If we to do our best to find a simple rule to split this data, we might well split by age, around 24 years old. And because most medal winners were over 24, the split would give us two sets of data. So what we've done is we're effectively trimming what we're looking at. If we know that nobody over the age of 24, most medals were over the age of 24, this split would give us two subsets of data. So we've got 18 to 24 here. Most of the time, there's one time here that somebody won a medal. And subset 2 is again around the border, 24, 25. That one doesn't have a medal, so that is slightly different. If we stop here with a simple model with one node and 2 leaves, leaf 1 contains non-medal winners and is 75% accurate on our training set. Leaf 2 contains medal winners and is also 75% accurate on the training set. Though we don't need to stop there, we can continue this process by splitting the leaves further. If in subset 1, the first new node could be split by weight, because the only medal winner had a weight less than people who didn't win a medal, the rule might start to begin with weight less than 65. So people with weight less than 65 are predicted to have won a medal, while anyone with a weight above 65 doesn't meet the criterion and might be predicted not to win a medal. So in subset 2, the second new node might be split by weight, but this time predicts that anyone with a weight over 70 would have won a medal, and while under 70 would not. So let's have a look at this. Yeah, this would provide us with a tree that could achieve 100% accuracy on this training set, using simply those 2 factors and those 2 boundaries. Decision trees are considered to have low bias, which means they're usually good at identifying features that are important in order to label something correctly. Yeah, we can do that, can't we? The major weakness of decision trees is overfitting. Yeah. Logically, you could keep subdividing and subdividing and narrowing down, but it would more and more fit your training set, so that when your testing set came in, it would have difficulty. So it must find the essential features. How we structure our decision tree is to avoiding its weaknesses. The deeper the tree, the more likely it is to overfit the training set. That kind of makes sense because you're asking more questions which are more and more linked to your training set. So you can probably identify every individual outcome in the training set by super overfitting it, by asking questions that effectively narrow each individual sample down to a leaf in a tree, in which case you've super overfitted that model. Other complex models often have similar weaknesses that can be mitigated through decisions about how they're structured or how they're allowed to be manipulated by the training. So let's have a look at decision trees and model architectures. Open our sandbox again. Decision trees and model architectures. We need a sandbox. Okay. Our goal in this exercise is to use a decision tree classifier to predict whether an individual crime will be resolved based on simple information such as where it took place and what kind of crime it was. These kinds of things was used to make predictions based of where a criminal might live. So, for example, if there is a whole spate of assaults or attacks on people, these things are usually done when somebody is very confident of their environment. They know where the alleys are, they know where the trees are, and they only know that if they kind of lived fairly locally or worked there very often. So by localizing where attacks occur, they can predict and have done very successfully many times roughly where someone's going to live, where that criminal is going to live. Very powerful idea. So let's load up our data in the usual way and then have a look at it, head and shape. So we'll have our first 5 rows and the basic shape of the whole data set. We've not split it yet into test and train. This is just the whole smash. It's a San Francisco crime. So these are our first values here. So these are the laws that are, this is the category of area about whether or not, and there's the districts, days of the week, resolution true or false, and we'll find out what X and Y mean. I think that is the X and Y coordinate of where the crime actually occurred. And then we've got our day of the year and time in hours. This is our first 5 rows, so this goes on the end of that. And our shape then is 150,000 rows with 8 columns. It's a lot of data. Not sure it's going to run that fast, but let's go. Now, data looks to be a mix of categorical variables like crime or PD district. And you know what we do categorical values? We tend to convert those into non-hot encoding. And numerical variables like day of the year and the time in hours, time of the day, and so on, refer to GPS coordinates and the resolution, which is our label. Resolution meaning not resolution of the map, but resolution as to whether or not the crime was solved. Okay. And we've got our X and Y GPS coordinates. Yeah, that's where we are. Let's visualize the data. Let's have a quick look to see what we're doing here. Multiple histograms against category, against resolution and district, resolution and location, and resolution and days of the week. I just want to make sure we got that the right way around here. Label X. Oh, sorry, that's the label of the whole lot. Yeah, okay. Let's load it up. Big data set. Might take some time to plot this. Still running. Oh, look at that. That was quick. And we haven't actually run the model yet, have we? This is just presenting the data. So this is whether or not the crime was solved or not, blue and red. Blue was not solved. And these are our category values. So here's a good one here. Nice picture of the different areas and whether a crime was solved or not solved in those areas. This is not a model, remember. This is simply the data. This is the raw data. This is what it's showing. And the coordinates over the town. So basically, this is the town, San Francisco Bay Area. Here. And everywhere there's a dot, there was a crime. So this is resolution whether, so This shows you whether the crime was solved or not. So resolution is false. Just want to make sure which is which. Put it over a red dot. Another red dot. So this is a crime that wasn't solved. The white crimes were solved. Yeah, in the white areas, they were solved. But in the red areas, they were not. And police forces up and down all around the world use this kind of stuff. It always pays to inspect your data before diving in. What can we see here? Most reported crimes were not resolved in 2016. Different police districts reported different volumes of crime. Different police districts reported different success rates. Friday and Saturday had more crimes. Larceny theft was overwhelmingly the most common crime reported. Yeah, violent crime, even in America, is not as widespread as a lot of people think. Although there's something like 100 million guns in the country. There you go. So let's one-hot encode. Yes, we remember how to do that. So our categorical features, we'll one-hot encode them. Drop first is false. So that means that we'll keep the index. Let's have a look. Yeah, we still keep the index. You can drop the first column if you want. And I have to do that every time I convert my arrays into NumPy arrays. You have to make sure that the index doesn't get carried across because it can make a right mess. So the head of the data set, there it is. That's our index. That's the categories for the crime. For the first 5, not particularly indicative data set. We'll also need to make a training and test set. Did you notice how much data we're working with before? If not, recheck the printouts from above. Yeah, 150,000 samples, a very large amount of data. Due to the sheer size, we can afford to have a larger proportion in the training set than we would normally have. Yeah, we can go right up to 10%. So we've got 90% in our training set and only 10% in our test set, because the test set really is kind of independent of the model. You just need to have a large number of samples, as large a number of samples as possible in your test set. You can vary that parameter based on the expected variance that you might get. Like, for example, the models I'm building at the moment using something called LDA coherence disturbance, is an idea I've come up with, will work out for a whole set of words the minimum number of questions that between them contain all of the words. And that is my test set effect, in effect. So instead of using all hundreds of questions, which will make the classification less crisp, it will make it noisy, I use exactly the right amount of data points, questions, that covers all of the possibilities. So you can be a bit smart in your design of your test and train. You need to be able to deal with the variance. So we'll fit this model. Several models here. So to maximize code reuse, we'll make a dedicated method that trains a model and then tests it. Okay, so here we are. We are going to define our own procedure that can fit and test a model. And then we'll simply call that procedure with our model, whatever that model is, and it will get the model. It's got some global features here. It's setting as a global variable the features, which means it's alive everywhere. It's not just local to this procedure. This means it can be changed anywhere. We're going to train and fit the model to the features, and we're going to train it with the resolution data. So that's the real value of resolution, whether a crime was solved or not. We're going to assess its performance with the accuracy there, using a balanced accuracy score based on the actual values and the predictions. Okay. And then we're going to run the testing. We get the test accuracy. Going to balance accuracy. Let's get this right. Score of the test resolution. So this is making our predictions based on the train resolution, and we're testing it based on our testing of whether or not the crime is resolved. So this is the actual value, and this is our predictions for it. And we retain the train accuracy and the test accuracy. So that's really testing how well our training set works with the model. Oops, make sure it didn't print anything. Nope. Still running. Print ready to go. Okay. So now we're going to use our decision tree calling our procedure to help us determine whether or not a crime will be resolved. Decision trees are categorization models that break decisions down into multiple steps. They can be linked to a flow chart with a decision being made at each subsequent level of the tree. So we're going to set our tree depth to be 3. That's our max depth there. And random state is what a random state is. So it's going to make a decision tree.
Steve, sorry, I'm a little bit behind. I'm getting errors in mine.
Above you, yeah. Oh, okay. Let's go back. Yeah.
So for me, just only the first one executed, unless I accidentally deleted something in the code.
Okay.
What was
Just
out?
go back to the top. Go back to the first thing that's done, which is here.
Yeah.
Decision trees and model architecture.
Yeah.
So just run that cell.
Yeah.
And then the one after that.
Yeah, this also ran, and then nothing up, and then I started to get errors.
Did you get the graph? Did the graphs come up? Because we're only plotting at this point. We're not doing anything to the data set.
Okay.
Did you get the bar charts here?
I got it for the first thing. Now I am getting error. So I guess I might have done something wrong here. So if I can look at the code, please, maybe.
Sure. Yeah.
I accidentally deleted something. Graphic. Numpy is there. Histograms. 2D multiple, histogram multiple, histogram. Delete data set. Yeah, I don't know what I deleted. So it ran first time. Now it's not running. Key error as error. Getlock. So base.py in getlock.
Oh, that means that there's a row missing that it's looking for. If getlock fails, it means it doesn't exist.
It's fine. I'll refresh it. Maybe
yeah, reload the data set.
Thank you. Yeah, thank you.
Yeah. Okay. But let's wait until you get that picture, and then we'll all move on together.
Sorry, it's still executing the second bit.
No, yeah, it's fine. It's fine.
Yeah.
Just need to get those 3 graphs.
Yeah.
Got that?
Yeah. Thank you.
Great. Let's move on. and we don't care about. Oh yeah, we need to get the data set. So we need to do the one hot encoding. So we'll run that again. If you've run that, just run that together. There's our one hot encoding. And then we want to, oh, key error. I've got the key error as well now. Trace back, drop first, false. Okay. So it didn't like, okay, let's go back. Okay. It's the last error that will tell you what's happening. None of index, category, district are in the columns. Oh, so what we've done is spelt one of them wrong, perhaps. So what we're looking for here is PD district and category.
I was talking to myself. Sorry. I
Right.
got here. Yes, same here. So
I've got the same error. So let's go back and check that PD district.
It's there, Steve. I think it has cached out. So if you look at the same error, I got confused. So the category and PD district are.
I'm gonna run it again. No, I still got the same error.
Yeah. So in the columns we can see, but the thing is, I think data set was cached. It was big or something, so it has got corrupted. So you might have to refresh it again, like I had.
I'll reload the data set.
Yeah. So refresh the page, and then it should be fine.
Yeah. Okay. Well, let's do it. Let's data set pandas read CSV. So that's what we're looking at. Run that again. And now go back to the next one. We've done that. Go to the next one. Is this graphing? We're not doing anything. We're just drawing histograms. So we don't care about that. And it's that's the one hot encoding that was the problem, wasn't it? And it was because it had forgotten the data set. Yeah, there we go. You're absolutely right. We needed to reload the data set. It decided to hash it away to save memory. So that's what we've got. And then we can move on to do our test split and show our shape. So there's our shape. We've got training is 135,000 by 387. And the testing is 15,000. So we're going to test it with 15,000 samples. That's quite acceptable. Model assessment code will fit several models here. So this is our user-defined function to pull in whatever model we want to use. And now it's ready to go. So we're going to go to our decision tree. And we're going to run a decision tree classifier. And then get our train accuracy and our test accuracy. That's a fit and test model of the model, which would be which gets returned by applying the decision tree. So what we're doing is we're saying how well our model, what we should come up with, fits the training data that we're put in. And then we're going to say how well the model fits the testing data. Because whatever the model is, we don't want it to overfit. We don't want it, ideally, it would be nice if the model had the same accuracy for test and train. That would be cool, because then we know that we've not overfit the model. So that's a good kind of indicator. Let's try it. So yeah, pretty good. The training accuracy is 0.68 and the test accuracy is 0.67. So as they're close together, you know that you've not really overfit the model. So that's not bad. Now the model is trained. Let's visualize it so we can get a better idea of how it works. And where it gets its tree moniker from. It's simple enough. You just actually plot the model, set the font size, what features are going to be called, class names here. So they're always in ascending numerical order in this case. We're going to label the first one as root, impurity as false, and so on. So this is the point at which it will do. It basically is going to do all of them. It's going to work in our particular area. There we go. So it's printed a very nice tree model. Something to put in a report there that would impress people. And it's quite possible, therefore, to follow this tree down. And you're going to come up with how many there are in the population, or each of the leaves at the end. So all of the code blue color boxes correspond to prediction that a crime would be resolved. So here, 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 and here. So if you manage to get down this route through there, through to there, and then through to there, you would be solved. You could be solved much faster if the number of warrants issued was less than 0.5. You can go straight in there. That blue and those two blue are solved. So if that's blue and that's blue, then that's always blue. This isn't quite certain. It needs to answer this question here. If there's other offences involved. If there's other offences, then you'll split that category again. Somebody who has other offences is very likely to be caught and very likely to be resolved. Best way not to get caught for a crime is to do it once in your lifetime and completely out of character with yourself. Unfortunately, the psychology of crime is that people think that the more they get away with something, the easier it's becoming. But actually, that's not true. It's becoming harder. The probabilities are stacking up against you. Right. All of the blue color boxes correspond to a prediction a crime would be resolved. Take a look at the tree to see what it thinks is important for predicting an outcome. Compare this to the graphs we made earlier. Can you see a relationship between the two? So the score we have is not bad, but the tree is pretty simple. Let's see if we can do better. Improving the performance through architecture. We'll try and improve our model's performance by changing its architecture. Let's focus on the maximum depth. So we set the maximum depth to 3 before, which meant it had to make some pretty wild guesses towards the end at the bottom of that. So now we're going to rerun the whole model and train it to be a very deep tree of 100 levels. Hopefully we're not going to print this. So our training accuracy is in danger of overfitting, get on to 100%, and our test accuracy is only 77%. So that's not awful, but it looks like it's been slightly overfitted. So you can imagine a tree with a maximum depth of 100 is big, too big to visualize. So let's jump straight into seeing how the new model works on our training data. Both the training and test accuracy have increased a lot. The training, however, has increased much more. Whilst we're happy with the improvement in test accuracy, this is a clear sign of overfitting because it's now predicting 100% of the training data, which is not good. We've actually here made the product the test. That's what we've done. So Overfitting with decision trees becomes even more obvious when we have more typical smaller sized data sets. Let's rerun the previous exercise, but only with 100 of the training samples. So basically, we are taking the first 100 rows of our training sample. That's what this is asking for. So train becomes train of the first 100 rows. Fit the model as before, do the print of the accuracy, and then train. So let's get this right. Oh, yeah, we need to obviously have saved the fact. Yeah, what we've done is we've temporarily saved our training set because we're going to modify it down here. So we've saved it here. And what we do is before we leave, we restore the train back to the full training set. The reason why we do that is because one, we don't care about memory, and two, it means that we can still keep the same names here for train and test and so on. We don't have to keep changing the names. So this is a common way of, if you like, temporarily saving this because you'll know you're going to want it back at the end. Let's run it. So training accuracy 1.0. Test accuracy, and that's with a depth of 100. So, but what's happening now is you've seriously overfitted the model. The model performs badly on the test data with reasonable sized data sets. Decision trees are notoriously prone to overfitting. In other words, they tend to fit very well the data they're trained on, but generalize very poorly to unknown data. It kind of makes sense that they would do that because it's a tree. It zooms in on the training data. It doesn't try and take them all into account and kind of try and find a nice aggregate balance between everything. It by definition zooms in on the training data. So you can see why, when you're only considering 100 samples, why it plummets through the floor. And it gets worse the deeper the tree or the smaller the training set gets. Let's see if we can mitigate this. We prune our tree. Interesting idea. Pruning is the process of simplifying a decision tree so it gives best classification results while simultaneously reducing overfitting. There are two types of pruning, pre-pruning and post-pruning. Pre-pruning involves restricting the model during the training so it does not grow larger than is useful. And we'll cover this below. So basically, areas that aren't getting you anywhere close towards a classification, you just lop them off. You can perform post-pruning is simply the tree after training it. It doesn't involve making of any kind of decision ahead of time, but simply optimizing the existing model. There's a valid technique, but it's quite involved. So what that's all about is saying we've got a completed model. So the pre-pruning idea is that we're going to limit the overall complexity by limiting the scope of what can happen as the model's being trained, as that tree is being constructed. It's like well, what they used to do to geisha girls in Japan, which was to bind their feet very firmly so that they didn't grow. It's the same sort of idea. You're pruning the basic tree to stop it growing out of all control. The other way, the post-pruning way, is much more intuitive, because what that is it produces the complete model and then looks at it and said, yeah, but all of that's going to get you nowhere. None of that is going to be involved in any kind of decision that's going to produce any kind of result. So we can safely take away that part of the model without affecting the overall quality of it. And the reason why you can get away with it, and this is what you have to see, is is there an alternative in the tree that can get you to that node? if there's another way through, then you can clip out the least kind of interesting or productive one. But you don't want to disable a leaf altogether from the bottom, because the problem with that is you've then lost some of your discriminating power. So it's an interesting topic area. So we can perform pre-pruning, generating many models, each with a different max depth. For each, we record the balanced accuracy of a test set to show it's important. Even quite large data sets will use 100 here. So let's have a look. Loop through each, build the model. Yeah, so what we're doing is we've got this max depth equals depth parameter every time we build the model, and we're going to run max depth over this range. So we're going to run it that many times each time with these values. And you do this to kind of investigate what scope overall the tree will produce. So let's run that. I think this will be fascinating. Yeah, there we go. So what we can say is this is our x coordinate, which is our depth, and this is our y coordinate, which is our accuracies for train and test. Okay, and what we're saying is when you start to up to about a few trees, they kind of track quite well, but overall are quite low. On the other hand, this is starting to overfit the model here. Because your test data seems to have leveled off. So we can see from the plot that the best accuracy is obtained for a max depth of about 10. So this is sort of here. This is when we've got quite high test values here. This is our best test result. And also at that point, the train isn't wildly different. So that's a nice point to operate your system on. As soon as you move beyond that, then your test actually goes down a little bit, but more importantly, your train starts to become overfitting. So this gives us a nice idea that we're going to get around 10 for our best accuracy for our final pruned tree. So we pruned the depth of the tree. Temporarily shrink the training set to 1/10,000 to see how the pruning is important, even with moderately large data sets. So we're going to run it again as pruned and not pruned. So previously we pruned it, and now we've got our max depth to set to be 10. So we're going to refit our final tree to print out its performance. Let's have a look. Oops. So unpruned, our train accuracy is way overfitting. Pruned at the level of 10, we have reasonably okay test accuracy. So our unpruned, that's the whole model. We've overtrained it, but we've got reasonable test accuracy. The question is, when we reduce it, the train accuracy, we look at the train accuracy at that point. So unpruned, the train accuracy is way overfit, and the test is 0.8. So that's not bad. The question is, the train is 0.8. So these between train and test, there's not that much of a difference, which is not bad. Not bad at all. So our new and improved model shows a marginally better balanced accuracy of the test set and a much worse performance on the training set than the model that is not pruned. This means our pruning has significantly reduced our overfitting. That's the point, without sacrificing much in terms of the test accuracy, because the test accuracy is actually gone from slightly increased, isn't it? It's slightly more accurate. But we need to probably test different numbers of samples to come to any conclusion. But the most important thing there is that we have reduced the overfitting by pruning the depth of the tree. Because what we've done is we've stopped it trying to completely explain the train data, because we don't want that. We want the most important characteristics of the train data. We don't want every single aspect of the train data broken down, because then the model we produced is the train data. When you've got that kind of accuracy, it pretty much is the training data. You may as well just use that rather than a tree. So our new and improved pruned model shows a marginally better accuracy and worse performance. Fair enough. If you would like, go back and change the number of samples to 100, and let's see how the max depth changes. Think about why this might be. Okay, let's do that. Let's go back and set the number of samples to be 100. Let's go back. So here, where it says train, make this 100. There. And let's see how we go. Change the number of samples to be 100. And find the optimal max depth. Is this the one that's going to plot? No, it's not on this one. It's the one before. So that's back. It's the one with the plot that we're looking at. So that is definitely the one before. This one here. So here we have here. We want to train that to be 100. Let's see what we get. Okay. Now, if we're only training it with 100 samples, we have slightly lower, below 10. But the problem is we've got a small number of samples, massive complexity in the model. Basically, the model is describing the samples. That's really what's happening there. And as a result, as we're only training it with 100, the test samples will contain new information that weren't available to the 100 in the sample. So what we've done is we've taken a small amount of training information and super overtrained on it. That's the point. And so it's really got no generalizability whatsoever, pretty much, with only 100 samples involved. So there's always a trade-off between complexity and sample size. And what you don't want to do is to have a small sample running with an overcomplicated model. It's far better in life to have a large number of samples and a much simpler model, because the much simpler model might well give you better results because it won't overfit the data. So we did the plot there. Go back. Let's have a look at the summary. marginally better, yeah. We went back, and so another option might be to play with how many features are entered into the tree. Similar patterns of overfitting can be observed by manipulating this. In fact, the number and type of feature provided to a decision tree can be even more important than its sheer size. Yeah, if you pick the right features, what you need is to pick features that divide logically the data to values that are intuitively for one thing or intuitively for another. If you can do that for your features and have less kind of features that are not so differentiated and distinguishable, then that produces kind of noise. So have a simpler model, but with really good features, with a lot of samples, with a fairly narrow depth. That's the visualization gives us that insight to gain insights into our data. We built a simple decision tree model, and we use that model to predict some labels. And then we found out that pruning a decision tree can reduce the effects of overfitting. So we're going to look at random forests and selecting architectures. So this is the same thing, but not with a tree, single tree. We're talking now about random forests. Now this is where it could get just a little complicated. So have a read. For the next few minutes.
Sorry, Steve, you're on mute.
Yeah, I was just talking about how bias can affect different situations. So how is a random forest trained? Branch of the random forest we looked at. How can I customize these architectures? We looked in there. So we're going to select our random forest architectures. And then we're going to see how we can change it and whether those changes are going to be maximum or minimal. So starting again with the pandas, improving everything. We need train test split. We're doing it with the San Francisco crime thing. We're looking by district. There are categorical features, so we'll need to encode those. Train and test and split it and look at the shape of it. Let's have a look. That's what we've seen before. Yeah, that's our data set. This doesn't look very promising for our first 5 rows, but it's just our first 5 rows. We say, just have to accept it. So these are our values. Let's move on. So this looks familiar. It is by now. We'll use the same model assessment code as we did in the previous one. So we've got our balance accuracy score. We're going to go through all of the columns and use our own user-defined function here for fitting and testing our model, which we've done. And we get our train accuracy, a test accuracy, and we return those 2 values. And this is going to be for, this is just a function at the moment. We haven't passed a model to it yet. So what we need now, whoops. Okay. What we need now is to pass our, so we're ready to go here. We need to pass our decision tree. Let's quickly train a reasonably well-tuned decision tree to remind ourselves of its performance. So we had a max depth of 10, which we knew was good, quite good value, quite a good value to use. So let's just check it because we're going to compare it to the forest. So the train is 0.7, test is 0.7, so not too badly overfitted there. Similar results for the train and test. And now random forest then is we're going to now bring our very simple forest with its default parameters, which is here we go. And we're going to train and test that. And print the accuracy. Fit and test model. So there we go. That's our user-defined function. And we're taking as a model parameter random forest. Okay. And then that's how we plan that. And that's what we've passed as a parameter to our train and test feature function. So our performance then, the train accuracy 0.8, test accuracy 0.7. So not as overfitted as it could be, but it's tending towards being slightly overfitted there, isn't it? So our 2-3 forest has done more poorly than the single tree on the test set, though this has done a better job on the train set. So it's, to some extent, this should be expected. Random forests usually work with many more trees. Simply having 2 allowed it to overfit the training data much better than the original tree. So if we went back here, our parameter, which we set for our random forest, was here. For the estimator, we've got 2. So we've got 2 trees in there. Let's build it several forest models, each with a different number of trees, and see how they perform. So this one is going to have estimator is n estimator, and we'll be running this for n estimator in n estimators, and n estimators is the set, the list 2, 5, 10, 20, and 50. So what this is going to do is to plot the values of our test accuracy and train accuracy for different values of trees in our forest. And we should be able to see what the best, or what might indicate a good number of trees to be by plotting our test and train accuracy against it. You know, ideally we want the train and test accuracy to be high together. That's what we're looking for. If the train accuracy is high and the test accuracy is low, we've overfitted. Still running. Very exciting. What do we think is the right number? What are we going to go for? 10? 10 trees in our forest? Is that going to give us our best results? Or will it be more? Yeah, what depth did we set the trees though? We set the depth of the trees. We haven't set the depth. Okay, so here we go. Here's our results. And we can see them, that the number of trees in estimators against the performance. Why are we looking at it twice? And this how our accuracy is here. So it levels off. Performance X number of trees. Performance X number of trees. Just can't quite understand why we've done it twice. Train and test, train and test. Oh, we only printed 2 values, perhaps. Hang on. Print, plot, number of trees estimators, accuracy for train and test. Oh, it's turned them into a dictionary. There we go. That's why we've got 2. We've got train and test accuracies twice. Okay, so the metrics look great for the training set, but not so much for the test set. More trees tended to help both, but only up to a point. Okay, so we just got a few more trees there, pretty marginal increase in return. We might have expected the number of trees to resolve our overfitting problem, but this was not the case. Chances are the model is simply too complex relative to the data, allowing it to overfit the training set. Yeah, basically the model, the model is too smart. It can take account of all the possible variances and changes in the test set and represent it, which is no good at all, because then it doesn't generalize to be able to handle the test set. It's always a compromise. So we can alter the number of parameters for the split parameter. So recall that decision trees have a root node, internal nodes, and leaf nodes, and that the first 2 can be split into newer nodes with subsets of data. Okay, so if we let our model split and create too many nodes, it becomes increasingly complex and starts to overfit. So it starts to try and design a model to fit the data, the training data. One way to limit that complexity is to tell the model that each node is to have at least a certain number of samples. Otherwise, it can't split into subnodes. Yeah. So what this is doing is saying I'm only going to allow successful nodes to propagate. It has to have, it can't just have no samples that pass it, because then everything after the bit is a waste, and it then restricts the range, the capture range effectively of the model, and it tends to overfit it. So that I like that idea. Certain number of samples, otherwise it can't split into subnodes. In other words, we set the model's minimum sample split parameter to be the least number of samples so that a node can be split. Well, the least number of samples is clearly 2. So you must have at least 2. I mean, when I'm clustering and writing clustering algorithms, I have the idea that a cluster has to have a minimum size of 3. If you're clustering lots and lots of items together, it can't really survive sensibly with less than 3. But this is saying obviously the minimum that you can set this is 2. Otherwise it can't split. In other words, we can set the model's minimum sample to the least number, which is 2. So models will quickly become too complex if the parameter is left untouched. Yeah, I mean, if you've got no minimum, it can just keep splitting and splitting and splitting, even though there's no sample that's ever been. It's then just sort of theoretically saying, well, yeah, I can split that, and there might be some in that value, so I'll split it for that one, and I'll split it for that one, and I'll keep going, even if there's no data that fits it. So this is, you have to be a little bit careful. We use the best performing model, then try it with a different minimal sample split. Well, our best performing model was 10, wasn't it? So let's find our minimum sample split. It's 2, 10, 20, 50, 100, and 500. Training it again. So we're going through a sequence again, and we're going to plot our test accuracy and train accuracy, etc. But this time for different samples of split. Now, interestingly, are we kind of... No, we're not, because what we're looking at here, by changing the number that it takes to be able to split, is the assumption that our test data is typical of our overall data, and so is our train. And of course, that's what we want. That's what we want it to accept. So the fact that we're making it harder for it to qualify to the next level is a good thing to do, generally. Let's try it, see what we get. Ooh, interesting. Very interesting. So the minimum samples, I don't think we got the parameter right there, right? Really? So our accuracy is falling down, because what it means is at 500 that we've just clipped it too much. We've cropped too much of the tree, so that it's not able to make sensible decisions, because it needs at least 500 of them to be able to meet whatever category it's got to gone into, whatever decision is made. It has to apply to at least 500 samples. And I know there's 150,000 samples altogether, but 500 is quite a large chunk of that. 100, it falls off. So here, but then the training accuracy, which is what you want. So what we're really looking for is the best compromise where the training, the testing and the training tracking each other well, but the accuracy of the against the test samples, which is really what it's all about, is not too low. So I would probably go for 100. Let's see what it says here. As you can see above, small restrictions of the model's complexity by limited size of split nodes reduce the gap between the training and test performance. This is subtle. It does so without damaging the test performance at all. By limiting the model complexity, we address overfitting, improving its ability to generalize and make accurate predictions. Notice using min samples 20 gave the best results. Did it? Hundreds? Well, it gave the best results for the test, for the train, but I think that's more indicating it's going towards overfitting, which is up here. With no minimum samples. So, okay, it's arguable, but 8 is okay. 20, I mean, gave us the best result for the test set, and the higher values worsened outcomes. Yeah, I think that's fair. And the other thing we can do, of course, is to change the depth of the model. Let's see how we're doing. Optimize model summary. Okay. So altering the depth, and our depth performance is here. So we're iterating through our max depths. What are we setting our... So we're still allowing, there's no minimum split here. So we're looking at the difference. Again, just this time only changing the parameter. Golden rule usually in any kind of investigation is that if you're looking for an effect, you must only change one parameter at a time. And that's effectively what's been done here. Here we go. So with different depths, it actually benefits from a higher value for max depth up to a limit of around 15, which is kind of here. So max depth gives you a better accuracy. Max depth of 15. As usual, it's important to evaluate different values when setting the model parameters. And of course, now we're going to do both. We're going to do, oh no, properly optimizing a model may take many hours to play around with. This is optimal. Optional, just note the model may take 1 to 2 minutes to train due to its size and the sheer volumes of the data. So this is using minimal sample slip 2. We thought that was the best results, but okay, maybe we're doing that next. And the minimum depth, sorry, maximum depth we set here to be 128. And the number of trees we set to be 200. And that is a very, very conservative thing to do. Just to say that there has to be only 2 samples for it to survive. In fact, I do that with my classifications when I'm looking for a keyword in a question. It has to be in at least 2 questions. Otherwise, I don't consider it to be discriminating enough. You know, I do lots of other tests as well, but if it doesn't exist in 2 questions, I throw it away. And that's really what this is kind of doing. This is saying it's got to carry at least 2 samples with it for it to be able to propagate. So let's run that. It may take a while. So this is going to now draw us a nice table with the column headings, model, train sensitivity, and test sensitivity. As we can see, fine-tuning the model's parameters resulted in a significant improvement in the test set results. And it is more than an art than a science in some respects. You just got to really think about the data, what you really want from it. But I can assure you there are algorithms out there that will automatically set those parameters to be the best values by running other kinds of tests. How are we doing? 1 minute 6. 10. Come on, we want to see this before we go home. 1 minute 34. 1 to 2 minutes. That's what you said? You think it's more? Here, no, 1 to 2 minutes. 1 minute 46. They're getting good, these guys, aren't they? So yeah, we've drawn our nice little panda frame. And we've got the model, decision tree, and the final random forest. And our training is 0.7 with our test of 0.7. So this final random forest we've done is significant improvement, but there's serious overtraining there, I think. So maybe we can run it again. What did we say our best value was for? Yeah, maximum depth. That's why, you see, the maximum depth of 128 is seriously overtrained that model, isn't it? That's what's done us. Let's see if it's any faster. We can do it again. Just change that value. The depth I thought we said was 10. And I thought our best value in terms of the number of trees was, I think, 20. And the minimum split we set was, I think, 10. And let's run it. Might be faster because we're not going so deep. There we go. Aha, see? So we're getting now a decision tree with good. It's very close. Not much in it really between our random forest. So we can play around and try and not overfit it, but get the values to be closer together. Okay, well, thank you for today. We'll come back tomorrow and look at hyperparameters in classification. That'll be interesting work. I'll see you tomorrow. Cheerio.
Thank you. Bye.
Thanks. Bye-bye.
Bye-bye.